What is the true shape of the universe? Is it a flat, infinite sheet, a giant cosmic sphere, or something even stranger, like a donut? This question has fascinated scientists and dreamers for centuries, and today, we're going to dive deep into the science behind it. To start, we need to understand a key concept, the curvature of spacetime. Albert Einstein's theory of general relativity tells us that mass and energy warp spacetime. Think of it like placing a bowling ball on a trampoline. The bowling ball creates a dip, or a curve, in the fabric of the trampoline. In the same way, galaxies, stars, and all the matter and energy in the universe curve the fabric of spacetime. The overall shape of the universe depends on how much stuff is in its total density. This leads us to a crucial number called the critical density. Imagine a cosmic balancing act. If the universe's actual density is exactly equal to this critical density, it means there's just enough matter and energy to keep it perfectly flat. In a flat universe, if you were to draw two parallel lines, they would stay parallel forever, never meeting and never drifting apart. This is the geometry we learned in school, Euclidean geometry. A flat universe would be infinite in extent. You could travel in a straight line forever and never return to your starting point. Now, what if the universe's density is greater than the critical density? In this scenario, there's so much gravitational pull that spacetime curves back on itself, like the surface of a sphere. This is what we call a closed or spherical universe. In this kind of universe, parallel lines would eventually converge and meet. And here's the mind-bending part. A closed universe is finite, but it has no edge. It's like walking on the surface of the Earth. You can walk forever in one direction and eventually you'll end up right back where you started, without ever hitting a wall or falling off an edge. So if you launched a spaceship in a straight line, it would eventually loop around the entire cosmos and arrive back at Earth from the opposite direction. Finally, what if the universe's density is less than the critical density? This means there isn't enough matter and energy to halt the expansion, and spacetime curves outwards, like a saddle. This is known as an open or hyperbolic universe. In a hyperbolic universe, parallel lines would diverge, moving further and further away from each other over time. Like a flat universe, an open universe is also infinite. You could travel forever without returning to your starting point. The geometry here is non-Euclidean and a bit trickier to visualize, but the saddle shape gives a good two-dimensional analogy. So we have three main possibilities: flat, closed, or open. How do scientists figure out which one is ours? They look for clues in the oldest light in the universe, the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Tiny temperature fluctuations in this ancient light hold the key. Imagine patterns of a known size in the early universe. Scientists can calculate how large these patterns, or hot spots and cold spots, should appear to us today depending on the universe's geometry. If the universe is flat, the light from these spots travels in straight lines to our telescopes, and they appear exactly the size we expect. If the universe is closed and spherical, it acts like a magnifying glass, making the spots appear larger than expected. If the universe is open and saddle-shaped, it acts like a demagnifying lens, making the spots appear smaller than expected. So what have our best telescopes, like the WMAP and Planck satellites, observed? Drumroll please. The data shows that, with incredible precision, the spots in the cosmic microwave background are the size we'd expect in a flat universe. The measurements are so accurate that they tell us our universe is flat to within a 0.4% margin of error. This means that on the largest observable scales, our universe behaves according to Euclidean geometry. Parallel lines stay parallel, and it appears to be infinite. Case closed, right? The universe is flat. Well, not so fast. Science is rarely that simple. The flatness we observe only applies to the portion of the universe we can see the observable universe. The observable universe is a sphere about 93 billion light-years in diameter, with us at the center. It's the region from which light has had time to reach us since the Big Bang, but what lies beyond that horizon, we simply don't know. It's possible that the entire universe is vastly larger than what we can observe, and we just live in a very flat-looking patch of it. Think about it this way: the Earth is obviously a sphere, but if you're standing in a small field, it looks perfectly flat. You can't perceive the planet's curvature over a short distance. In the same way, the universe could be a giant sphere or some other complex shape, but it's so immense that our observable bubble looks flat to us. The theory of cosmic inflation, which suggests the universe underwent a period of hyperfast expansion right after the Big Bang, actually predicts this. Inflation would have stretched the universe so much that any initial curvature would be flattened out, at least within our observable horizon. This brings us to an even wilder idea: topology. Geometry tells us about the local curvature of spacetime, but topology describes its overall global shape and connectedness. Even if the universe is geometrically flat, it could have a non-trivial topology. For example, it could be a torus, which is the mathematical name for a donut shape. Imagine you're living on the surface of a giant, three-dimensional donut. The universe would still be locally flat. Small triangles would still have angles that add up to 180 degrees, but globally it would be finite and connected in a peculiar way. If you traveled far enough in one direction, you'd loop back to your starting point. If you traveled up, you might reappear from below. This would create some strange visual effects. If we looked out into space with a powerful enough telescope, we might see multiple images of the same galaxy at different stages of its life appearing in different parts of the sky as its light takes various looped paths to reach us. Scientists are actively searching for these kinds of repeating patterns in the cosmic microwave background and galaxy surveys. They're looking for what they call circles in the sky, pairs of matching circles in the CMB temperature map that would be the telltale sign of a finite, topologically complex universe. So far, the search has come up empty, placing limits on how small such a donut universe could be. If our universe has a weird topology, it must be on a scale larger than our observable horizon, which means we might never be able to directly prove it. So, what is the true shape of the universe? The best evidence we have points to a universe that is geometrically flat on the largest scales we can measure. This suggests it's likely infinite. However, we can't rule out the possibility that we're living in a tiny, flat-looking section of a much larger, curved cosmos, and we can't yet dismiss the mind-bending possibility that our universe has a complex topology, looping back on itself in ways we can't yet detect. The quest to map the cosmos is one of the grandest adventures in science. Every new telescope and every more precise measurement of the cosmic microwave background brings us closer to an answer. But for now, the ultimate shape of everything remains one of the most profound and tantalizing mysteries out there. Thanks for joining me on this cosmic journey today. If you enjoyed this exploration of spacetime and the universe's ultimate form, don't forget to hit the like button and subscribe for more deep dives into the biggest questions in science. Let me know in the comments what you think the universe's shape is. See you next time.